Hello, tonight we are going somewhere most people never think to look. Not up towards stars or skylines or anything built to impress. Down, beneath the floorboards, beneath the foundation, beneath the soil itself where something ancient has been running a civilization far longer than ours, without language, without light, and without mercy. Termites. Say the word, and most people picture an exterminator's van parked outside a neighbor's house. A nuisance, a pest, something dealt with, sprayed away, forgotten. But that picture is wrong. What lives beneath your feet, beneath forests, savannas, and yes, suburban homes, is one of the most sophisticated biological machines ever produced by evolution. A colony that thinks without a brain, builds without a blueprint, wages chemical warfare without a general, and has been doing all of it for over 250 million years, longer than the dinosaurs, longer than flowering plants. Tonight we are going to spend time with this empire. All of it, the engineering, the chemistry, the destruction, the society, and finally, the strange, humbling truth that the creature eating your home alive may also be holding the planet together. 100 facts, 5 stages, 1 underground world you never knew existed. Let's go down. Termites are older than almost everything you have ever called ancient. The earliest termite fossils date back over 250 million years, placing them firmly in the Triassic period before the first dinosaur took a single step. While most of the creatures alive at that time are now compressed into rock and memory, termites survived. They survived the mass extinction that ended the Permian. They survived the asteroid that erased the dinosaurs. They survived ice ages, continental drift, and the slow, violent rearrangement of every landmass on Earth. And through all of it, they kept building. The species you find in your wall today is not some evolutionary footnote. It is the living product of a design so effective nature has seen no reason to significantly alter it in 250 million years. That is not luck. That is engineering so precise it became permanent. When scientists find termite fossils, they are often struck by how familiar the specimens look. The same body plan, the same social structure, the same basic architecture. Some solutions, it seems, are simply correct. A single termite colony is not a group of insects living together. It is a city. Some species, particularly the giant mound-building termites of Africa and Australia, house populations that rival major metropolitan areas. A mature colony of Macrotermes bellicosus, one of the most studied species on Earth, can contain upward of 5 million individuals in a single, interconnected structure. 5 million, all coordinated, all working, all blind. To hold that number in your mind, consider this: that is roughly the population of Los Angeles packed into a structure you could walk past on a hiking trail without a second glance. And unlike a city, there is no mayor, no city council, no central planning office. Every decision where to build, what to repair, who to feed emerges from the collective behavior of individuals who have no idea what the whole is doing. Scientists call this emergent intelligence. It is one of the most baffling phenomena in all of biology. The mound itself is a skyscraper, not metaphorically, structurally. The towering clay structures built by African and Australian termite species reach heights of over 9 meters in the largest recorded specimens. To put that in terms, a person can feel that is taller than a standard 2-story American home and built entirely without tools, without hands, and without eyes. Every grain of soil is carried moistened and placed with the termite's mandibles and body bonded with saliva and fecal material into a composite material that, when tested by engineers, rivals the compressive strength of low-grade concrete. The mound is not a pile. It is a structure with chambers, corridors, load-bearing columns, and ventilation systems, and it rises from a creature roughly the size of a grain of rice. The ratio of body size to construction height is proportionally the equivalent of a human being constructing a freestanding tower nearly 2 kilometers tall with nothing but their mouth and their hands. What you see above ground is the smallest part. Most people, if they encounter a termite mound, assume it ends at the soil line. It does not. The visible mound is essentially the chimney, the exhaust structure of a much larger system below. The true colony extends meters beneath the surface, through a branching network of tunnels and chambers that can stretch horizontally for distances that would take a person several minutes to walk. In some documented colonies, the underground tunnel network covers an area larger than a standard American football field, all excavated grain by grain, all sealed against the outside world. These tunnels connect foraging sites, food storage chambers, nurseries, the royal chamber and fungal gardens, each zone purpose-built, each maintained at its own specific temperature and humidity. The mound you see is in a very real sense just the tip. The empire is underground, invisible, and almost certainly closer to your feet than you would prefer to think. The walls of a termite mound are not just hard, they are engineered. Material scientists who have studied termite mound composition have found a construction logic that goes well beyond accident. The outer shell of the mound is dense and compacted, built to shed rain, resist erosion, and deflect heat. The inner walls are thinner and more porous, built for gas exchange and temperature modulation. The termites don't alternate these materials consciously. They respond to local chemical and physical cues, placing denser material where stress accumulates, thinner material where airflow is needed. The result is a gradient structure, exactly the kind of layered composite design that human engineers spend careers trying to optimize. Researchers at several universities have directly modeled termite mound wall architecture to improve insulation materials for buildings in hot climates. The termite, it turns out, solved a problem that stumped our best materials scientists, and it did so without a single equation, diagram, or engineering degree. The temperature inside a termite mound is by almost any measure remarkable. In the tropical and subtropical regions where the largest mound-building species thrive, outside temperatures can swing dramatically from searing midday heat to cool nights, from dry season to monsoon. The interior of the mound holds steady. Researchers measuring the core temperature of active macrotherms mounds have found internal readings maintained within approximately 1 degree of 30 degrees Celsius, day after day, season after season. That is a level of thermal stability that most human homes with their insulation and climate systems struggle to match. The mechanism is entirely passive, no energy input required. The mound's architecture creates a natural convection current, drawing cool air up from the deep underground chambers and releasing heat through the upper vents. It is a system so effective that it inspired the passive cooling design of the Eastgate Center in Harare, Zimbabwe, a large commercial building engineered to function without conventional air conditioning. Termites are among the most powerful geological forces on Earth, and almost no one talks about them. Every year, across tropical and subtropical ecosystems, termite colonies collectively move an estimated 10 tons of soil per hectare. That figure comes from aggregated field studies conducted across Africa, South America, and Southeast Asia, and it places termites in rarefied ecological company alongside earthworms as one of the only invertebrates capable of reshaping the physical structure of the land at a landscape scale. They don't just dig, they sort. They bring mineral-rich subsoil to the surface, deposit organic material deeper, and reroute water through their abandoned tunnels. Over centuries, termite activity measurably changes the composition and fertility of the soil above their colonies. Geologists studying ancient termite mound sites have found chemical signatures in the soil that persist for thousands of years after the colony is gone. These insects are not just living in the landscape, they are slowly and continuously remaking it. A termite mound breathes, not as a metaphor, as a measurable physical process. The mound is equipped with a network of ventilation shafts that function with striking similarity to a biological respiratory system. Warm, carbon dioxide-rich air produced by millions of metabolizing bodies rises through the core of the mound. As it ascends, it passes through a network of thin-walled upper passages where gas exchange occurs. Carbon dioxide diffuses out, oxygen diffuses in through the porous mound surface. Cooler oxygenated air then descends through peripheral channels back to the colony below. The cycle is continuous, passive, and precise. It requires no mechanical assist, just architecture. And the termites adjust it. When carbon dioxide levels rise too high, workers add material to constrict certain passages. When oxygen drops, they open others. They are, in effect, performing real-time respiratory therapy on a structure the size of a small shed using only their bodies and a sensitivity to atmospheric chemistry that we are only beginning to understand. Some termites build using a compass. In the flat, sun-baked grasslands of northern Australia, the magnetic termite Amitermes meridionalis constructs mounds of a deeply unusual shape, tall, thin, and blade-like. These structures are oriented with extraordinary consistency, their broad faces pointing east and west, their thin edges pointing north and south. The alignment is so precise that early European explorers used the mounds as navigation aids. The function is thermal. The broad eastern face catches the low morning sun, warming the colony quickly after cold nights. As the sun climbs and the heat intensifies, the thin profile minimizes the mound's exposure to peak midday radiation. By afternoon, the broad western face absorbs the gentler declining heat. The termites have, without any understanding of solar geometry, produced an architecture that solves it perfectly. Scientists still debate whether this orientation is encoded genetically learned from the colony or self-organized through individual responses to heat gradients during construction. Termite mounds have survived what human buildings have not. Construction equipment operators in Africa and Australia have reported needing multiple passes, sometimes with heavy machinery, to demolish large, mature termite mounds during land clearing operations. The structures resist because they have been built and rebuilt over generations, each layer reinforcing the last. Each repair made with material slightly better adapted to local conditions than the one before. Some mounds have been radiocarbon dated and found to be over 1,000 years old. That means there are termite constructions standing on Earth right now that were already old when Columbus was born, that predate most European cities in the Americas, and that have been continuously inhabited and maintained ever since. No architect oversaw them. No government funded their upkeep. They persist because the colony persists, repairing damage, adjusting structure, and building forward into a future no individual termite will ever live to see. The outer shell of a termite mound is waterproof. Not water-resistant, waterproof. In regions where seasonal rainfall arrives in violent, sustained downpours, the mound's exterior surface sheds water the way a roof sheds it. Researchers who have analyzed the outer layer of mounds built by Macrotermes species found a dense hydrophobic surface created by the specific ratio of clay particles, organic binders, and saliva compounds the termites use during exterior construction. Water beads and runs off rather than soaking in. This matters enormously because a mound that absorbs heavy rain would soften, collapse under its own weight, and kill the colony. The termites have solved this problem with a material that took human builders centuries of trial and error to approximate, and they renew it continuously after every rainstorm. Workers inspect the exterior and patch any surface compromise before the next rainfall arrives. Think of it as a roofing crew that never sleeps, never builds, and never misses a damaged shingle. A termite colony does not stay in one place. It expands. As a colony matures, it pushes outward, constructing satellite chambers connected to the central mound by sealed underground highways. These extensions allow the colony to access food sources too distant for daily foraging trips, establish secondary nurseries, and distribute population pressure across a wider area. In some well-documented African colonies, the satellite network extends so far from the central mound that a person standing at the outermost chamber would have no idea there was a mound nearby. The whole system, central structure, peripheral chambers, connecting tunnels, functions as a single distributed organism. Food collected at the edges is transported inward. Eggs produced at the center are distributed outward. Chemical signals flow in both directions simultaneously. It is in every meaningful sense a city with suburbs built underground, invisible from the surface, and expanding quietly in every direction. Every worker termite is blind, not partially sighted, not light sensitive. Blind, completely lacking functional eyes. The workers who excavate kilometers of tunnel, carry soil grain by grain, construct geometrically consistent chambers, and maintain a structure housing millions. Do all of it in total darkness with no visual information whatsoever. Their world is chemical and mechanical pheromone trails. Vibration signals humidity gradients and tactile contact with nestmates and surfaces. What makes this extraordinary is the consistency of the output. Researchers who have mapped termite tunnel systems using three-dimensional imaging have found a geometric regularity that would be impressive from a sighted tool-using builder. Corridor widths are maintained, chamber proportions repeat, structural supports appear at load-bearing intervals. None of this was designed. All of it emerged from millions of blind individuals, each responding to the same chemical and physical cues, producing collectively an architecture that looks very much like it was planned. Termites have directly influenced the design of human skyscrapers. This is not a loose metaphor, it is documented engineering history. The passive cooling system of the termite mound, in which convection currents circulate air without mechanical energy, has been studied and directly applied in architectural practice. The Eastgate Center in Harare, Zimbabwe, designed by architect Mick Pierce in collaboration with engineering firm Arup, explicitly drew on termite mound ventilation principles to create a building that maintains comfortable interior temperatures without conventional air conditioning. In a climate where outdoor temperatures fluctuate dramatically, the building uses roughly 10% of the energy a conventionally cooled structure of the same size would consume. It was not the last. Subsequent research projects in the United Kingdom, Australia, and the United States have used computational models of termite mound airflow to develop next-generation building ventilation standards. The termite did not know it was consulting, but the field of biomimicry engineering inspired by nature owes it a considerable debt. The foundation of a termite mound goes deep. While the visible tower draws the eye, the underground anchor that supports it extends downward with equal ambition. In large macrotermes colonies, excavation teams have traced the mound's foundation to depths exceeding 3 meters below the soil surface. At those depths, the colony accesses moisture that surface-level droughts cannot reach, a critical survival advantage in the arid and semi-arid regions many large mound-building species inhabit. The deep foundation also anchors the structure against wind and surface erosion with a stability that pure surface construction could never achieve. Think of it in terms any American homeowner would recognize: the ratio of above-ground structure to below-ground foundation in a termite mound significantly exceeds the standards required by most municipal building codes for residential construction. The termite, with no knowledge of soil mechanics or structural engineering, intuitively solved the foundational problem that every tall structure built on Earth must eventually answer. Some termite mounds are older than the United States. Radiocarbon dating of several large mound complexes in Africa and South America has returned ages exceeding 1,000 years, and in a handful of cases closer to 4,000. These are not abandoned ruins. They are active living colonies, continuously inhabited, continuously maintained, and continuously expanding. The mound you date to 1,000 years ago was not built by the termites alive in it today. It was built by their ancestors, extended by their predecessors, and repaired by every generation in between. What persists is not the individual, but the structure and the chemical identity of the colony that occupies it. In this sense, a termite mound is less like a building and more like a city, one where the stones outlast every citizen who ever walked its corridors. And the institution survives because the next generation always knows exactly what to do. Termites feel the world shake and they respond. In the absence of sight, termites have developed an acute sensitivity to substrate-borne vibration. When a section of the mound is disturbed by a predator, a rainstorm, or structural stress, nearby workers detect the vibration through organs in their legs and immediately begin repair behavior. No alarm pheromone is required. No nestmate needs to carry the message. The vibration itself is the signal. Researchers have demonstrated this by playing recordings of termite distress vibrations through speakers placed against mound walls, triggering repair responses in workers who had no other indication anything was wrong. The system is fast, precise, and requires no central coordination. Each individual responds to local information. The repair happens because enough individuals in enough places all respond to the same signal at the same time, and together they fix what none of them understood was broken. The scale of termite construction relative to body size has no human equivalent. Consider the numbers not as digits, but as distances you can feel. A worker termite is roughly 4 to 6 millimeters long. The mound it helps build can reach 9 meters in height. That ratio, body length to structure height, is approximately 1,500 to 1. Applied to a human body of average height, that ratio would produce a freestanding structure nearly 2.5 kilometers tall. The tallest building ever constructed by humans, the Burj Khalifa in Dubai, stands less than 1 kilometer high, built with cranes, steel-engineered concrete, and a workforce of hundreds of thousands of specialized sighted tool-using humans working from detailed architectural plans. The termite uses mandibles, saliva, and soil. It has no plan, it has no foreman, and proportionally it builds taller. A termite mound is never finished. Unlike a human building which reaches completion and then simply ages, a termite mound is in a permanent state of construction. New chambers are added as the colony grows. Old corridors are sealed when no longer needed. Damaged walls are repaired within hours. Ventilation shafts are widened in summer and narrowed in winter. The structure is a living document continuously rewritten by a colony that has no memory of its original form and no blueprint for its future shape. What guides the additions is not a plan, but a set of responses to population pressure, to temperature, to humidity, to damage, to chemical signals from the queen. The mound you see today is not the mound that existed a decade ago, and the mound a decade from now will not be this one. It grows the way a living thing grows, not toward a design but toward survival. The combined weight of a termite colony exceeds that of every large mammal sharing its ecosystem. This fact stops most people cold, and it should. In the tropical savannas and forests, where large mound-building termite species thrive, biomass studies have consistently found that termite colonies collectively outweigh the lions, elephants, buffalo, and antelope living in the same area combined. The numbers vary by region and season, but the pattern holds across multiple independent studies conducted in Africa, South America, and Southeast Asia. It is a statistic that quietly reframes the entire savanna. The animals we photograph, track, and name, the megafauna that define our image of wild Africa, are in terms of sheer biological mass secondary characters. The dominant organism in that landscape is underground, invisible, and has been there since before mammals existed. That is not a footnote. That is the headline. And we have been misreading the story for a very long time. Termites live in a world built entirely from chemistry. Where humans navigate by sight reading, faces, signs, landscapes, termites navigate by molecule. Every interaction in a termite colony, from the most routine work assignment to the most urgent military response, is mediated by chemical signals so precise, so layered, and so fast that they constitute a communication system more sophisticated than most people would ever guess from looking at an insect the size of a grain of rice. Pheromones guide workers to food. Pheromones assign caste identity. Pheromones declare war, signal danger, announce death, and regulate reproduction. The colony's entire social fabric is woven from invisible chemistry, a language with no alphabet, no grammar, and no ambiguity. When researchers first began mapping termite chemical communication in the mid-20th century, the complexity they found surprised even the entomologists who had spent careers studying social insects. The more they looked, the more channels they found: layered signals, contextual meanings, molecular dialects that varied between species and even between colonies of the same species. A single pheromone molecule can start a war. When a termite soldier detects a threat, a breached tunnel wall, an invading ant, a predator's vibration, it releases an alarm pheromone into the air of the gallery. That molecule spreads through the enclosed space at a speed determined by diffusion and airflow. Within seconds, every termite in the affected zone has received the signal and begun responding. Workers retreat. Soldiers advance. The response is not staged or discussed. It is immediate, coordinated, and collective, triggered by a quantity of chemical that would be invisible to any instrument the naked eye could use. Studies have timed the alarm cascade in controlled laboratory settings and found that a colony of several million individuals can shift from foraging behavior to full defensive posture in under 60 seconds from the release of a single to-alarm signal. No army in human history has ever achieved that mobilization speed at that scale, and no general has ever given an order that small. A termite trail is not approximate, it is molecular. When a foraging worker finds a food source and returns to the colony, it lays a trail pheromone on the substrate, a chemical pathway that nestmates can follow back to the source. What makes this extraordinary is not the concept which is shared with ants, but the precision. Laboratory studies using high-resolution tracking have shown that subsequent workers following a termite trail do not merely travel in the general direction of the chemical, they follow the exact path molecule by molecule with a DA, spatial accuracy measured in fractions of a millimeter. The trail is not a scent cloud. It is a line, a precise chemical instruction embedded in the substrate, readable only to the species that wrote it, and accurate enough to guide millions of workers through complex underground terrain without a single wrong turn. Scientists have described it as the closest natural equivalent to a printed circuit, a physical pathway that carries information in one precise direction. Some termite soldiers explode. This is not hyperbole, and it is not rare. Several termite species, most notably those in the genus Neocapritermes found in South American and Caribbean forests, have evolved a defense mechanism with no equivalent in the animal kingdom. Older worker soldiers in these species develop specialized glands in their abdomen that accumulate a toxic adhesive secretion over the course of their lives. When threatened by a predator or enemy colony, the termite contracts its body wall with sufficient force to rupture itself, literally detonating, spraying the accumulated toxin outward in a radius that immobilizes or kills attackers. The sacrifice is total and deliberate. The individual dies. The colony survives. Researchers who first documented this behavior named it autothysis, from the Greek, for self-sacrifice. It is in the truest biological sense a living weapon that chooses to fire itself. And the older the soldier, the more toxic the payload, suggesting the colony ages its weapons intentionally. The exploding termite's weapon keeps working after the termite is gone. The toxin released by autothysis is not simply a chemical irritant that dissipates in seconds. Studies of the secretion produced by Neocapritermes taracua, one of the most thoroughly documented exploding termite species, found that the compound remains biologically active and physically adhesive for a significant period after release. It immobilizes ants and other small arthropods on contact, binding their mouthparts and legs with a sticky matrix that hardens on exposure to air. In field observations, researchers found dead and immobilized attackers at blast sites hours after the termite soldier had detonated, meaning the weapon continues to defend the colony long after the individual who fired it has ceased to exist. From a purely military engineering standpoint, this is a remarkably sophisticated outcome. A sacrificial weapon with both immediate and delayed effect, manufactured biologically, deployed autonomously, and calibrated over millions of years of evolutionary pressure to be exactly as lethal as the colony needs it to be. Termites invented agriculture millions of years before humans did. Deep inside the mounds of the most advanced termite species, particularly those in the subfamily Macrotermitinae across sub-Saharan Africa and South and Southeast Asia, there are gardens, not metaphorical ones, actual cultivated gardens of a specific fungus, Termitomyces. The termites harvest plant material, chew it into a spongy substrate, and inoculate it with fungal spores, creating a carefully maintained growing medium that the fungus colonizes and digests. The termites then eat the fungal growth. This relationship, a mutual dependency between termite and fungus, refined over an estimated 30 to 50 million years, predates human agriculture by an almost incomprehensible margin. The earliest evidence of human farming dates to roughly 10,000 years ago. Termites were cultivating Termitomyces when the continent still wore their ancient shapes. Scientists still debate the precise evolutionary origin of this partnership, whether the fungus domesticated the termite or the termite domesticated the fungus, or whether the answer, as with most things biological, is far more complicated than either. The fungal garden is a feat of climate control. Termitomyces, the fungus that Macrotermitinae termites cultivate, is extraordinarily sensitive to environmental conditions. It requires a narrow temperature range, precise humidity, and carefully managed airflow to grow productively. The termites maintain all three, not with instruments but with architecture and behavior. The fungal garden chambers are positioned at specific depths in the mound where temperature is naturally stable. Workers continuously monitor humidity by direct contact with the fungal mass and adjust the porosity of surrounding walls by adding or removing material. Ventilation to the garden is managed separately from the colony's general airflow system. When researchers have artificially altered the temperature or humidity of a garden chamber, workers respond within hours, restructuring the surrounding architecture to restore the preferred conditions. They are in effect running a controlled environment greenhouse without any understanding of what a greenhouse is or why the one they are running works. Termites are their own pharmacists. The saliva that termites use as a construction adhesive is not only structural, it is medicinal. Analysis of termite saliva compounds has identified a suite of antifungal molecules specifically active against the mold species most likely to contaminate the Termitomyces garden. Workers apply this saliva to the garden substrate during routine maintenance, not in response to visible contamination, but as a preventive measure. The result is a garden that remains remarkably free of competing fungal species, despite existing in an environment warm, humid, nutrient-rich underground chambers that would normally be a paradise for mold. The termites have, through millions of years of chemical evolution, produced a pharmaceutical compound precisely targeted at the pathogens most threatening to their food supply, and they apply it prophylactically before illness appears, which is a level of medical sophistication that in human terms took us until the 20th century to consistently achieve. The queen controls reproduction chemically across the entire colony. In a colony of several million individuals, only one termite reproduces the queen. This is not enforced by guards or physical barriers, it is enforced by chemistry. The queen continuously produces a cocktail of pheromones that, when distributed through the colony via physical contact and shared food chemically, suppresses the reproductive development of every worker and soldier. Their gonads remain dormant, their bodies remain developmentally arrested. The queen's pheromone is in effect a colony-wide contraceptive broadcast, maintaining her reproductive monopoly over millions of individuals simultaneously with no enforcement mechanism other than the molecules themselves. When researchers have experimentally removed the queen from a colony and replaced her pheromone with a synthetic version, the colony continues to behave normally. Workers keep working, soldiers keep guarding, until the synthetic supply is interrupted. At that point, the colony begins producing replacement reproductives within hours. The queen does not rule by force, she rules by chemistry. And the chemistry, while she lives, is absolute. When the queen dies, the colony feels it almost immediately. The queen's pheromone does not linger. It requires continuous production and continuous distribution, and the moment her body stops producing it, the chemical signal begins to fade from the colony's environment. Workers who have been in direct contact with her body are the first to notice their behavior shifts within minutes of her death. Within hours, the pheromone gradient across the colony has weakened enough that developmentally suppressed reproductives begin to change. Their bodies, released from chemical arrest, start producing their own reproductive hormones. Within days, a new cohort of potential queens and kings emerges. The colony's internal succession protocol, triggered not by a vote, not by hierarchy, but by the simple, irreversible fading of a single chemical signal. It is one of the most elegant succession mechanisms in the natural world, and it raises a question that researchers have genuinely wrestled with: if the colony responds this immediately and this precisely to the queen's death, in what sense is it ever truly unaware of her? Termite tunnels are coated in a living chemical map. Every surface inside an active termite colony is not merely structural, it is informational. Workers deposit a thin layer of material along tunnel walls as they travel a mixture of fecal matter, saliva, and cuticular compounds that collectively encode a staggering amount of colony-specific data: the identity of the colony, the location of food sources relative to the current position, the traffic density of different corridors, The proximity of the royal chamber. Termites moving through these tunnels are not navigating by memory. They are reading the walls, extracting positional and social information from the chemical coating with every step through sensory organs on their antennae and legs. When researchers chemically sterilize sections of termite tunnel, removing all deposited material, workers entering those sections slow down, lose directional consistency, and begin exploratory behavior as though encountering unknown territory. The map was not in their heads, it was on the walls. And without it even familiar, ground becomes foreign. Termites can smell an enemy colony and seal the door. Individual termite colonies produce a colony-specific chemical signature, a blend of cuticular hydrocarbons that functions as a kind of molecular identity card. Every member of the colony carries this signature on their body, acquired through contact with nestmates and the colony environment. When workers detect foreign chemical signatures in their tunnel network indicating that a rival colony has breached their territory, they respond with immediate architectural intervention. Passages leading toward the incursion are sealed with fresh construction material within hours. In some species, soldiers are stationed at the sealed point, while workers build a permanent wall behind them. The detection is purely chemical, no visual confirmation, no auditory signal, just the presence of a foreign molecular identity where a familiar one should be. It is border security without borders, a perimeter, defined not by walls but by chemistry, and defended the moment that chemistry is violated. Termite soldiers carry a signal that overrides the instinct to flee. In any animal, including humans, the instinct to escape danger is among the most powerful biological drives. Termite workers are no exception. When alarm signals flood a gallery, the workers' first chemical instruction is to move away from the threat. But soldiers release a secondary pheromone, a stand-fast signal that chemically counteracts the flight response in workers nearby. Under its influence, workers stop retreating. Some begin repair behavior, sealing breach points, even as soldiers fight in front of them. Others carry eggs and larvae away from the danger zone in an orderly withdrawal rather than a rout. The soldiers hold, the workers work. The young are protected. The whole response is not commanded by any individual, it is the result of two competing chemical signals resolving in real time into a coordinated military and civilian response. No general issued those orders. The chemistry wrote the battle plan, and every termite in the gallery followed it without knowing they were following anything at all. Some termites are chemical spies. In the long evolutionary arms race between termites and ants, two of the most socially complex insect groups on Earth, certain termite species have developed a weapon more subtle than soldiers or toxins. They produce pheromones that mimic the chemical signature of ant species that share their habitat. Workers of these termite species can move through ant foraging territory without triggering alarm responses because to the ants' chemical senses, they smell like ants. The mimicry is not perfect, and it does not work indefinitely, but it buys enough time for foraging workers to collect food and retreat before the deception is detected. Researchers studying this phenomenon in Southeast Asian species have found that the mimicry compounds are synthesized in specialized glands and are not present in colony members who never leave the mound. The termites, it seems, produce their disguise only in the individuals who need it, manufacturing a chemical costume precisely targeted at the predator most likely to encounter the wearer. Termites are changing the atmosphere one gut at a time. Every termite colony is collectively a methane production facility. The microbial community inside the termite hindgut, a dense ecosystem of bacteria, archaea, and protozoa, breaks down cellulose through a fermentation process that releases methane as a byproduct. Individually, the quantity is negligible. Collectively, across the estimated 250 million metric tons of termite biomass on Earth, the contribution is measurable. Various studies have estimated that termites contribute somewhere between 2 and 5% of global annual methane emissions, a figure that has been debated, revised, and contested for decades. With scientists still working to pin down the precise contribution across the enormous variety of species and habitats involved. What is not debated is the basic chemistry. Every termite gut every day is running a fermentation reaction that releases a greenhouse gas. The insect that eats your home is also in a very small way warming the planet it lives on. Though it has been doing so, It should be noted for considerably longer than we have. The termite gut is the most complex microbial ecosystem ever found in an insect. When researchers first began using modern genetic sequencing tools to catalog the microbial community inside termite hindguts, the results were by the standards of the field astonishing. A single termite hindgut, a structure roughly the size of a poppy seed, contains over 200 distinct species of bacteria, archaea, and single-celled eukaryotes, many of them found nowhere else on Earth. These organisms work in metabolic sequence, each one processing a compound produced by the previous passing, the result to the next in a biochemical assembly line of extraordinary efficiency. The final product is a set of simple sugars and fatty acids the termite can absorb and use for energy. Without this community, the termite cannot digest wood at all. It is not an optional enhancement, it is the core of the termite's entire ecological identity. Remove the gut microbiome and the termite starves on a diet of pure wood within 2 weeks. The insect and its passengers are metabolically speaking a single organism. Termites produce hydrogen and use it. Among the many byproducts of the termite hindgut fermentation process, one stands out for its sheer energy density: molecular hydrogen. The cellulose fermenting bacteria in the termite gut produce hydrogen as a metabolic waste product, and other organisms in the same gut community immediately consume it. Hydrogen-consuming archaea use it to reduce carbon dioxide into methane. Other bacteria use it in separate reduction reactions. The result is a closed internal economy in which a high-energy molecule produced as waste by one organism is immediately captured and used by another with almost no loss. Researchers studying this process have described the termite hindgut as one of the most hydrogen-efficient biological reactors known to science. Its hydrogen to methane conversion rate exceeds that of most engineered industrial fermenters. Biotechnology companies have, for this reason, studied termite gut chemistry as a potential model for biofuel production. Trying to replicate in a laboratory setting what a 5mm insect has been doing effortlessly for 250 million years. A termite's fate is decided by chemistry before it is born. Termite colonies maintain their carefully balanced population of workers, soldiers, and reproductives, not through deliberate planning but through chemical regulation of larval development. The pheromones present in a larva's environment during its early development, particularly those derived from the queen from soldiers and from the existing worker population, influence gene expression in ways that permanently redirect the larva's developmental trajectory. A larva exposed to high concentrations of soldier pheromone during a critical developmental window will develop into a soldier regardless of its genetic potential to become anything else. The decision is irreversible. Once the developmental window closes, the caste is fixed. The colony does not decide what it needs and then produce it. It produces a chemical environment that shapes what it gets. It is in effect an epigenetic factory using chemistry to manufacture the precise social composition the colony requires, adjusted continuously in response to losses, growth, and environmental pressure. Scientists have weaponized termite chemistry against termites. The trail pheromone of the eastern subterranean termite, one of the most economically destructive species in North America, was identified, isolated, and synthesized by researchers in the 1990s. The compound called Z-Dodec-3-ene-1-ol turned out to be extraordinarily potent. Quantities too small to weigh on a standard laboratory scale are sufficient to trigger following behavior in thousands of workers. Once synthesized, the compound was incorporated into commercial bait systems, devices that use the termite's own trail signal to lure workers toward a slow-acting toxicant, which they then carry back to the colony and share through trophallaxis. The result is a delivery mechanism that uses the colony's own communication system to distribute poison through its population. The termite's chemical sophistication, the very thing that makes it so effective as a builder and forager, becomes the vector for its own elimination. It is one of the more elegant ironies in applied entomology. Termites can find water they have never touched. In arid environments where surface water is absent for months at a time, termite colonies maintain the humidity levels. Their fungal gardens and developing larvae require drawing moisture from sources deep below the soil surface. The mechanism involves humidity-sensitive receptors located on the termite's antennae, capable of detecting vapor pressure gradients across extremely small distances. Workers follow these gradients downward, excavating toward increasing humidity with no prior knowledge of what lies below until they reach the capillary fringe above the water table, where they can access moisture directly. In some documented cases, termite colonies in African savannas have been found accessing water at depths of 30 to 40 meters below the surface, drilling in effect their own wells through solid soil, guided by nothing more than the molecular weight of water vapor drifting upward through the ground. When you consider that the termites doing this work are blind, silent, and smaller than your fingernail, the achievement becomes quietly extraordinary. Termites have a word for death, and they act on it immediately. When a termite dies inside the colony, its body does not remain where it falls. Within minutes, nestmates detect a suite of chemical compounds, fatty acids produced by the decomposing body, and begin removal behavior. The dead termite is carried to a designated waste chamber, or ejected from the colony entirely, before decomposition can progress far enough to introduce pathogens into the population. Researchers have identified the primary death signal as oleic acid, a compound released by cellular breakdown, and demonstrated its power by painting live, healthy termites with it. The painted termites, chemically indistinguishable from corpses, were picked up by nestmates and carried to the waste area, despite walking, moving, and attempting to resist. They were in every observable sense alive. But they smelled dead. And in the termite's chemical world, smelling dead and being dead are the same thing. The living termite carried protesting to the refuse pile, was released only when it had groomed enough of the oleic acid from its body to smell like itself again. The termite alarm system is faster than most vertebrate reflexes. Speed matters in defense, and the termite colony has optimized for it with a ruthlessness that is almost mechanical. The chemical alarm signal travels through enclosed gallery space at a rate governed by molecular diffusion and airflow, reaching individuals meters away within seconds of release. Meanwhile, the neural response in a termite soldier, from chemical detection at the antenna to physical action, has been measured in laboratory settings at under 50 milliseconds. 50 milliseconds is faster than the blink of a human eye. It is faster than the withdrawal reflex that pulls your hand from a hot surface. The termite does not deliberate. It does not assess. The moment the molecule arrives, the response is already executing. Multiplied across thousands of soldiers receiving the same signal simultaneously, the result is a defensive activation that appears to any observer nearly instantaneous. An ant colony that breaches a termite gallery does not encounter slow, disorganized resistance. It encounters something that was already ready before the breach was complete. A termite trail can outlast the termite that laid it. Under controlled laboratory conditions, researchers studying trail pheromone persistence placed termite trail secretions on glass surfaces and then removed all termites from the area. They returned at intervals to test whether foraging workers introduced later would still follow the trails. The results were striking. Trails remained detectable and followable by termites for periods exceeding 24 hours after deposition, and in some lower temperature conditions significantly longer. In the field, this persistence means that foraging routes established by previous shifts of workers remain legible to the next cohort without any overlap or handoff. The colony's foraging network does not require continuous maintenance to remain functional. The chemical infrastructure persists between uses like roads that repair themselves simply by being traveled each new pass, refreshing the signal for the next. It is a communication system with built-in redundancy, requiring no server, no relay, and no individual who remembers where the path leads. Some termites attract their own predators deliberately. Among the more counterintuitive findings in termite chemical ecology is the discovery that certain species produce compounds that attract natural predators of their enemies. When facing a sustained assault from a particularly aggressive ant species, some termite colonies release volatile chemicals that draw in predatory insects and arthropods that prey specifically on those ants. The termites do not benefit directly from the predator's presence. The predator is not an ally and may itself pose some risk to the colony, but the net effect is a reduction in the attacking force. The termite's chemical release shifts the local predator-prey dynamic in its favor without requiring any direct confrontation. Researchers who documented this behavior described it as a form of indirect defense, using the ecosystem's own food web as a weapon. It is in strategic terms remarkably close to what military theorists call using a third party to relieve pressure on a contested front. The termite arrived at this strategy without a war, college, a general, or a map. Scientists still debate whether termite pheromone networks constitute a form of memory. The question sounds philosophical, but it is a live issue in contemporary behavioral biology. A termite colony, through the cumulative deposition of pheromones on tunnel walls, food sources, and nestmates, creates a chemical record of its own recent history. Where workers have traveled, where food has been found, which corridors carry high traffic, which chambers are occupied. This information is not stored in any individual brain. No termite remembers anything in the conventional sense. But the information exists encoded in chemistry, distributed across the physical structure of the colony. New workers entering the system can read it. Decisions emerge from it. The colony behaves differently because of it. Some researchers argue this constitutes a genuine form of external memory cognition offloaded from individual minds into the physical environment. Others maintain it is simply stimulus-response behavior with no cognitive content whatsoever. The debate remains unresolved, and it raises a question worth sitting with quietly if the outcome is indistinguishable from memory. Does the mechanism matter? Termites cost the world more money than almost any other animal on Earth. Every year, the global economic toll of termite damage to human structures is estimated at roughly $50 billion. That figure encompasses direct structural repair, preventive treatment, lost property value, and the cost of monitoring programs in high-risk regions. To hold that number in proportion, it exceeds the annual gross domestic product of several small nations. It exceeds what many countries spend on their entire public infrastructure maintenance budgets. And it accumulates quietly, not through dramatic visible events like fires or floods, but through slow, invisible consumption happening inside walls, beneath floors, and within the wooden bones of structures that appear from the outside, entirely intact. Insurance adjusters, structural engineers, and pest control professionals who work with termite damage regularly describe the same experience, opening a wall that looks perfectly normal and finding nothing behind it, just hollow air where solid wood used to be. The destruction is not loud. It never announces itself. It simply continues until the day it cannot be ignored. In some regions, termites destroy more than fire and flood combined. The comparison is not rhetorical. It comes from damage cost analyses conducted in termite endemic regions, particularly parts of Australia, Southeast Asia, and the southeastern United States. In Queensland, Australia, studies conducted in the early 2000s found that termite damage costs exceeded the combined annual insurance payout for fire and flood damage in the same region. In parts of the American South, Louisiana, Florida, South Carolina, termite remediation costs in urban areas consistently outpace fire damage repair in years without major natural disasters. This disparity exists partly because fire and flood, while catastrophic, are visible and insurable. Termite damage is neither. It develops over years, remains hidden until advanced, and is explicitly excluded from most standard homeowners insurance policies on the grounds that it constitutes a preventable infestation rather than an unforeseen event. The logic of that exclusion to anyone who has opened a termite-damaged wall can feel like a very dark kind of humor. A mature termite colony eats without stopping. 24 hours a day, 7 days a week, every day of the year, a mature subterranean termite colony forages, harvests, and consumes. There is no dormant season. There is no overnight pause. Worker termites operate in continuous shifts, with no individual working indefinitely, but the collective effort never ceasing. The result, in practical terms, is that a large, established colony can consume approximately 0.5 kilogram of wood every single day. Over the course of a year, that is enough to hollow out a substantial structural timber. over the course of a decade, which is well within the lifespan of a single colony. It is enough to compromise the structural integrity of an entire room's worth of framing. The damage does not feel urgent because it is not urgent in any single moment. It is the accumulation of millions of small invisible acts, each one negligible, all of them together devastating. It is in the most literal sense death by 1,000 bites. Termites eat your home from the inside out and leave the outside perfect. The foraging strategy of subterranean termites is not random. It follows the grain of the wood, consuming the soft cellulose-rich interior while leaving the harder outer surface largely intact for as long as possible. The result is a structural timber that, tapped with a knuckle from the outside, sounds solid. Painted over, it looks solid. Load-bearing, it holds until it doesn't. Structural engineers who specialize in termite damage assessment have developed a standard field test. They drive a screwdriver blade into a suspect timber with light hand pressure. In sound wood, the blade meets resistance. In termite-damaged wood, it sinks sometimes to the handle into a hollow shell that has no interior left to speak of. The wood has not been removed. It has been consumed, converted into energy, inside a termite gut, and the empty space left behind is sealed from view by the thin, intact surface the termites strategically preserved. It is camouflage they did not intend, and it is devastatingly effective. The organisms doing the actual digesting are not the termites themselves. This is one of the more philosophically interesting facts in termite biology, and one that quietly undermines the intuitive image of the termite as destroyer. When a worker termite ingests wood, it cannot digest cellulose on its own. Its own enzymes are insufficient for the task. The actual breakdown of cellulose into usable sugars is performed by the microbial community in the termite's hindgut. The bacteria, archaea, and protozoa, catalogued in an earlier fact, working in coordinated metabolic sequence. The termite provides the wood and the gut environment. The microbes do the chemistry. The termite absorbs the products. It is a partnership so ancient and so complete that neither partner can survive without the other. Newborn termites must acquire their gut microbiome by consuming the feces or saliva of older nestmates, a process called proctodeal, trophallaxis. Without this inoculation, they starve. The creature dismantling your home is in a very real sense a vehicle, a mobile, armored housing unit for the actual agents of destruction, which are microorganisms too small to see. Subterranean termites never need to surface, and that is precisely what makes them so dangerous. The most destructive termite species in North America, the eastern subterranean termite and the Formosan subterranean termite, spend their entire working lives below ground or inside wood. They do not expose themselves to light or dry air. They travel from their underground colony to their food source, through sealed tunnels pressed against foundation walls, through cracks in concrete slabs, through expansion joints, and through the soil itself, arriving inside a structure's wooden framing without ever crossing a surface a homeowner might notice. A pest control professional inspecting a home for termite activity is not looking for termites. They are looking for the subtle secondary signs, the faint mud traces, the slightly soft baseboard, the hairline crack in a foundation wall that has been subtly widened from below. The termite itself will likely never be seen until the inspection uncovers it. It has no reason to be visible. Visibility, for a soft-bodied, moisture-dependent insect operating in a world full of predators, is simply another word for death. Mud tubes are one of the most remarkable structures in the insect world. When subterranean termites need to cross an exposed surface, a concrete foundation wall, an open stretch of masonry, a gap between soil and wood, they do not cross it openly. They build a tunnel first. Mud tubes, also called shelter tubes, are sealed passageways constructed from soil particles, fecal material, and saliva, roughly the diameter of a pencil, that allow termites to travel across otherwise inhospitable surfaces while maintaining the darkness and humidity their bodies require. Workers construct them from the inside, extending the tube forward grain by grain as they advance. A mud tube pressed against a foundation wall is the most common visible evidence of subterranean termite activity, and finding one is rarely good news. What the tube represents is not an exploratory probe. It is a finished highway. By the time a mud tube is long enough to be visible to a homeowner, the colony that built it has almost certainly already found what it was looking for on the other end. Termites can enter a structure through a gap thinner than a business card. The physical threshold for subterranean termite entry into a structure is genuinely difficult to defend against. Research measuring the minimum gap width that foraging workers can exploit has found that openings of approximately 1 millimeter, roughly 1/32 of an inch, are sufficient for worker access. 1 millimeter is thinner than a standard business card. It is a gap that exists routinely at the junction between a concrete foundation and a wooden sill plate, at plumbing penetrations, at conduit entries, and at virtually every point where a structure meets the ground. Building codes in termite endemic regions specify treatments and barriers precisely because the architecture of a standard American home, wood framing, resting on a concrete foundation, creates termite entry opportunities at almost every point of contact between the two materials. There is no construction method that eliminates these gaps entirely. The best current practice manages them. It does not eliminate them. The termite, working with a body designed over millions of years to find exactly these openings, finds them anyway. Termites will eat things that are not wood. Cellulose is the target, not wood specifically. Cellulose is the structural polymer found in plant cell walls, and it appears in a remarkable range of household materials beyond timber. Cardboard boxes stored in a basement or crawl space are to a termite an easily accessible cellulose buffet. The paper facing on drywall, the thin layer bonded to the gypsum panel, contains cellulose and is regularly consumed by termites working behind finished walls. Books, cotton-based fabrics, certain carpet backings, insulation materials with paper facings. Some species have been documented consuming the outer sheath of underground utility cables not for the cellulose, but because the material softens with age and the termites remove it while excavating. The practical implication is that a termite infestation in a home is not limited to structural damage. Everything stored near an active infestation, particularly anything kept in cardboard, is potentially at risk. The termite does not distinguish between your house and everything in it. Standard homeowners insurance does not cover termite damage almost anywhere. This fact lands differently when you are standing in a home with compromised structural framing. In the United States, Canada, Australia, and most of Europe, termite damage is classified by insurance providers as a maintenance issue, a preventable infestation resulting from inadequate inspection or treatment, rather than an unforeseen, catastrophic event. It is therefore excluded from standard property insurance policies with the same categorical clarity as general wear and tear. The financial exposure this creates for homeowners in termite endemic regions is substantial. A single severe infestation requiring structural repair, replacement of compromised sill plates, floor joists, wall framing, and subfloor can cost tens of thousands of dollars entirely out of pocket. Pest control warranties exist and provide some protection, but they typically cover retreatment rather than repair costs. The economic reality is that termite damage in most jurisdictions lands entirely on the property owner, quietly, expensively, and without warning. A home can be structurally compromised by termites with no external sign whatsoever. This is not an exaggeration used to sell pest inspections. It is a documented reality that structural engineers and pest professionals encounter regularly. Because subterranean termites consume wood from the interior work within wall cavities and underfloors, and seal their entry points with mud to maintain humidity. The surface presentation of a termite-infested home can be entirely unremarkable. Paint intact, floors level, walls solid to the touch, no visible mud tubes, no discarded wings, no live termites in plain sight. The damage, when finally revealed, typically during renovation, sale, inspection, or catastrophic structural failure, can be severe enough to condemn sections of the structure. Cases documented in Florida, Louisiana, and Hawaii describe load-bearing walls that had been reduced to hollow shells over periods of 5 to 10 years, with no indication visible from either the interior or exterior of the home. If you live in a termite-endemic region and have never had a professional inspection, the absence of visible signs is not reassurance. It is simply the nature of the damage. The Formosan termite arrived in America, hidden in the cargo of war. Following the end of World War II, military equipment and supplies were shipped back to the United States from the Pacific Theater, including wooden packing crates, pallets, and ballast material from ports in Taiwan, Japan, and the broader Pacific region. Embedded in that material, undetected by any inspection protocol of the era, were colonies of Coptotermes formosanus, the Formosan subterranean termite, one of the most aggressive and destructive termite species on Earth. The insect established itself first in port cities New Orleans, Houston, Charleston, Honolulu, and spread steadily outward from there. By the time its presence was formally recognized and its destructive potential understood, it had already colonized significant portions of the Gulf Coast. Today, the Formosan termite is established across at least 13 American states and Hawaii, and pest control researchers consider it effectively impossible to eradicate from the regions it occupies. Another quieter one fought inside the walls of American homes had just begun. A single Formosan colony operates at a scale that redefines the word infestation. Standard eastern subterranean termite colonies in North America typically contain between 60,000 and 200,000 individuals, already a formidable destructive force. A mature Formosan subterranean termite colony can contain upward of 2 million workers. The foraging range of a Formosan colony extends significantly farther than that of native species. Its consumption rate is proportionally higher, and unlike many termite species that maintain a single primary nest, Formosan colonies frequently establish secondary satellite nests called carton nests within the walls and roof spaces of infested structures entirely above ground, independent of soil contact. A home hosting a mature Formosan colony is not hosting a pest infestation in the conventional sense, it is hosting a city, one that is consuming the building it occupies around the clock in numbers that make the standard chemical treatment protocols developed for native species look at best optimistic. Termites have started fires. The connection between termites and electrical fires is not theoretical, it is documented across multiple countries and building types. As termites excavate through wall cavities, they occasionally encounter the plastic or rubber insulation surrounding electrical wiring. While they do not eat the insulation intentionally, it contains no cellulose. They remove it as an obstruction during excavation, exposing bare conductors within wall cavities. Exposed conductors in proximity to the dry, frass-filled tunnels that termites leave behind create conditions for arcing and ignition. Fire investigators in Australia, Southeast Asia, and the American South have attributed confirmed structural fires to termite-compromised wiring in cases where no other ignition source could be identified. The termite does not intend to start a fire. It is pursuing cellulose with the same blind chemical persistence it brings to everything else. But the consequence, a home that burns from the inside, from a cause that was never visible on the surface, is one of the more sobering illustrations of what an invisible infestation can ultimately produce. Termites multiply the damage they cause long after they have moved on. The destruction a termite colony inflicts on wood is not limited to the material the termites actually consume. As workers excavate tunnels through structural timber, they compromise the wood's ability to shed moisture. Rain and humidity penetrate through entry points the termites have created. The damp wood becomes colonized by wood rot fungi organisms that require pre-existing moisture pathways to establish. The fungi soften additional wood beyond the termite galleries. That softened wood attracts further termite foraging. The cycle termite damage enabling fungal rot. Fungal rot enabling further termite access can accelerate structural deterioration far beyond what either agent would cause alone. Structural assessors who work in humid climates describe a pattern they encounter routinely, a termite infestation that has been active for 3 years, leaving damage consistent with 7 or 8 years of decay, because the secondary rot has multiplied the primary destruction several times over. The termite does not just eat your home, it opens the door for everything else that will. Hawaii is the most termite-damaged place in the United States, by a significant margin. The islands of Hawaii present a confluence of conditions that termite species find in every sense ideal. Warm temperatures year-round, high ambient humidity, abundant rainfall, dense urban construction in close proximity to tropical forest, and a history of international shipping that has introduced not one but multiple invasive termite species to an island ecosystem that evolved without them. Hawaii hosts several destructive termite species simultaneously, subterranean drywood and dampwood species operating in the same structures, sometimes in the same walls. The per capita cost of termite damage in Hawaii consistently exceeds that of any continental American state. Honolulu, in particular, has been the subject of ongoing pest management research for decades, with some studies estimating that a significant proportion of older residential structures in the city show active or prior termite activity. The island's isolation, which once protected their ecosystems, now works against them, and introduced species once established has nowhere further to spread and no natural check on its population. Termites are one of the primary threats to Angkor Wat, and have been for centuries. The temple complexes of Angkor, built between the 9th and 15th centuries in what is now Cambodia, survived jungle, encroachment, war, neglect, and centuries of abandonment in remarkable condition. The stone structures themselves are largely intact, but the wooden elements, interior fittings, support structures, secondary buildings, storage facilities have fared less well, and termites are a primary reason. Conservation teams working at Angkor have documented active termite colonies in and around the temple complex, with damage to both surviving wooden elements and to the root systems of trees that have grown into and around the stone structures over centuries. The relationship between Angkor and termites is not a recent problem. Historical records and biological evidence suggest it has been ongoing since the structures were first built. The greatest architectural achievement of the Khmer Empire has outlasted every human threat it faced. The termite patient and invisible remains. A termite can destroy a load-bearing beam while leaving its paint perfectly intact. This fact is worth dwelling on because it speaks directly to why termite damage is so consistently advanced by the time it is discovered. The foraging strategy of subterranean and drywood termites prioritizes the interior of structural timber, following cellulose-rich growth rings inward, while leaving the denser outer wood and any applied surface finish largely undisturbed. A painted timber that has been heavily damaged internally will present no visual indication of compromise, no cracking, no staining, no surface irregularity, until the remaining shell fails under load. Structural engineers documenting termite-related building collapses have found cases where a beam reduced to less than 20% of its original solid mass was still supporting the structure above it, not because it was structurally sound, but because nothing had yet applied sufficient force to complete the failure. The building was in effect already gone. It simply had not fallen yet. That distinction between structural failure and visible collapse is one that termites exploit with a consistency that has no parallel in the world of structural damage. You can hear termites eating if you know how to listen. Active termite galleries within structural timber produce a faint but detectable acoustic signature. The mandibular action of workers harvesting wood, rapid, repetitive, mechanical, creates a clicking or rustling sound at frequencies audible to the human ear under quiet conditions. Pest professionals and experienced homeowners who know what to listen for describe it as a faint, dry ticking like the sound of static heard through a thin wall, or a very quiet crumpling of paper happening somewhere inside the structure. The sound is easiest to detect at night when ambient noise is lowest, and by pressing an ear directly against a wall baseboard or floor in an area of suspected activity. Acoustic detection has in fact been formalized as a professional inspection technique. Electronic stethoscopes and acoustic emission sensors are used by some pest management professionals to detect termite activity inside walls without destructive testing. The termite that makes no visible announcement of its presence does, it turns out, make a sound. A very small, very patient, very constant sound. Scientists still debate whether termites can distinguish structurally critical wood from expendable material. The question has practical implications and no clean answer. Field observations in heavily infested structures have occasionally suggested that termite damage clusters in non-structural elements, furniture trim subfloor, while adjacent load-bearing timbers remain relatively intact. Some researchers have proposed that termites may respond to the compression stress in loaded timber, which alters the wood's density and moisture content in ways that could theoretically be detected chemically or mechanically. Others maintain that the apparent selectivity is coincidental, a product of foraging patterns and moisture gradients rather than any assessment of structural function. Controlled laboratory studies have produced inconsistent results, with some showing termite preference for unloaded timber and others showing no preference at all. The honest answer, as of current research, is that we do not know. What we do know is that when termites do attack a load-bearing element, which they do routinely, in infested structures worldwide, they are entirely indifferent to what that element is holding up. The termite queen is the longest-lived insect on Earth. Most insects measure their lives in weeks or months. The mayfly lives for a single day as an adult. A worker honeybee survives 6 weeks in summer. Even the longest-lived social insect, queens of certain species, rarely exceed 30 years. The termite queen stands apart. In several Macrotermes and Reticulotermes species, queens have been documented surviving for 30 to 50 years in laboratory conditions, with some field estimates based on colony age assessments suggesting lifespans approaching that range in the wild. 50 years. In an animal with no spine, no immune system in the vertebrate sense, and a body plan unchanged for 250 million years. To place that in human terms, a termite queen that hatched the year you graduated high school could still be alive, laying eggs and running a colony when your grandchildren are born. She is not merely old by insect standards, she is by almost any biological measure one of the most durable reproductive machines evolution has ever produced. The queen's body becomes something barely recognizable as an insect. A newly mated termite queen begins her reproductive life at roughly the same size as a large worker, a few millimeters long, unremarkable in appearance. Over years of continuous egg production, her abdomen swells with the physiological demands of laying tens of thousands of eggs per day. In mature Macrotermes queens, this process produces an abdomen that can reach 8 to 10 centimeters in length, roughly the size of a human index finger, while the head, thorax, and legs remain at their original dimensions. The result is a body so disproportionate that the queen cannot move under her own power. She lies in the royal chamber surrounded by workers who groom her, feed her, and carry away her eggs as quickly as she produces them. She has not moved independently in years. She may not move again. Her entire existence has been redirected by biology, by chemistry, by the needs of the colony, into a single biological function. She is, in the most literal sense possible, a living egg factory. And she is the most important individual in an empire of millions. The queen lays an egg approximately every 2 seconds. The reproductive output of a mature termite queen is measured against body size without parallel in the animal kingdom. A large Macrotermes queen produces between 20,000 and 30,000 eggs per day, a rate that works out to roughly 1 egg every 2 to 3 seconds, sustained continuously around the clock for decades. To contextualize that output, a single queen, over the course of a 30-year lifespan, could theoretically produce over 300 million eggs. Not all survive, not all hatch, not all develop, but the sheer volume of production ensures that colony losses to predation, disease, and environmental stress are continuously replaced, and that the population grows steadily year after year as long as the queen lives. The workers who attend her cannot keep pace individually. Eggs must be moved by continuous relay teams passed from worker to worker toward the nursery chambers in a stream that never stops. The queen does not pause. The colony does not pause. The only thing that ends this is the queen's death, and the colony has a plan for that too. The king is one of biology's most overlooked figures. In almost every popular account of termite society, the queen receives the attention, the swollen body, the extraordinary lifespan, the staggering reproductive output. The king is rarely mentioned. He should be. Unlike the queens of bee and ant colonies who store sperm from a single mating event and use it over their entire reproductive lifetime, the termite queen is fertilized repeatedly and continuously by a king who remains beside her in the royal chamber for her entire life. The king does not die after mating. He does not leave. He stays groomed, fed, and sustained by workers for decades, fertilizing the queen regularly to maintain the fertility of her egg production. He lives nearly as long as she does in the same chamber, performing the same function invisible to almost every account of termite society ever written. It is in the natural world one of the longest and most consequential partnerships between two animals, a quiet, lifelong collaboration conducted in total darkness, deep underground, sustaining an empire neither of them will ever see. Termite workers are neither fully male nor fully female. The worker caste, the blind, soft-bodied individuals that constitute the vast majority of any termite colony, occupies a biological category that does not map cleanly onto standard sexual categories. In most termite species, workers are individuals whose reproductive development has been chemically arrested at an early stage. They possess the genetic material for either sex, but have been prevented by the queen's pheromone environment from developing functional reproductive organs. They are in developmental terms suspended, capable of redirected development under the right chemical conditions, but fixed in their current form as long as those conditions persist. This developmental flexibility is one of the colony's most powerful, adaptive tools. A worker is not locked into its role by irreversible biology, it is held there by chemistry. Change the chemistry, and the worker can become something else. The colony does not maintain its caste structure through rigid genetics. It maintains it through a continuous chemical conversation, one that is always in every direction, subject to revision. The termite colony has no leader and functions better because of it. This is perhaps the most disorienting fact in termite biology for a human mind to absorb. We are a species that organizes around hierarchy, commanders, managers, presidents, foremen. We find it almost impossible to imagine a complex enterprise running without someone in charge. The termite colony runs without anyone in charge. The queen does not issue instructions, the soldiers do not receive orders. The workers do not report to a supervisor. Every behavior in the colony, every construction decision, every foraging route, every defensive response emerges from individuals responding to local chemical and physical information with no knowledge of the colony's overall state and no awareness that their actions are part of a coordinated whole. The result, somehow, is coordination. The result, somehow, is architecture. The result, somehow, is a civilization that has outlasted nearly everything that has ever lived on this planet. What humans achieve through hierarchy and planning, termites achieve through chemistry and emergence. And looking at the mound they build standing taller than your house, older than your country, it is genuinely difficult to argue that our approach is superior. Damage to the mound is repaired before any individual termite understands it has occurred. When a section of mound wall is breached by a predator, a rainstorm, or a researcher's deliberate intervention, the repair response does not begin with an assessment. No termite surveys the damage, calculates what is needed, and directs others to the site. Instead, workers in the immediate vicinity of the breach detect changed conditions, a drop in humidity, an increase in airflow, a shift in the vibration signature of the surrounding structure, and begin depositing material. Their behavior attracts other workers whose own deposits attract more. The repair grows not because anyone planned it, but because each new worker responds to the same local cues that triggered the first. Within hours, a breach that would take a human crew days to properly assess and repair has been sealed, reinforced, and smoothed back into the mound's surface. The colony did not decide to fix it. The colony simply fixed it. And somewhere in the distinction between those two things lies one of the deepest questions in the science of collective behavior. Termite soldiers are fed by the workers they protect because they cannot feed themselves. The soldier caste represents one of evolution's more consequential traits: to produce soldiers capable of defending the colony with oversized heads, enlarged mandibles, and in some species, the chemical weaponry described earlier. The colony sacrifices those individuals' ability to feed independently. Soldier mandibles in most species are too large and too specialized for the delicate work of harvesting and ingesting food. Soldiers are entirely dependent on workers for nutrition, receiving pre-digested food through trophallaxis mouth-to-mouth transfer at regular intervals. This dependency is total and lifelong. A soldier separated from workers will starve within days. In return, it provides the colony with a specialized defensive capability that workers with their smaller, more generalist bodies cannot replicate. The arrangement is a biological contract, complete specialization on both sides, mutual dependency enforced by anatomy, and a division of labor so absolute that neither party could survive a single week without the other. It is in its way a perfect partnership. Built entirely on need, a termite larva's destiny can be rewritten almost until the last moment. The developmental plasticity of termite larvae is one of the more remarkable features of the colony's organizational biology. Unlike the rigid caste determination of some social insects, termite larvae pass through a series of molts, during which their developmental trajectory remains to varying degrees adjustable. A larva moving toward worker development can be redirected toward soldier development if the colony's soldier population drops below a critical threshold detected chemically by the larvae themselves through pheromone ratios in the environment. The redirection requires hormonal changes that the larva initiates in response to that chemical signal. It does not require instruction from any other individual. The larva reads the colony's needs from the chemical environment around it and adjusts its own development accordingly. In some species, this flexibility persists through several larval instars, meaning a larva that has already begun developing worker characteristics can still be redirected. The colony does not assign roles, it creates conditions, and the larvae reading those conditions assign themselves. Some colonies keep a spare queen hidden, waiting chemically suppressed. In several termite species, the colony maintains a cohort of individuals called secondary or neotenic reproductives, undeveloped, potential queens and kings, whose reproductive development has been partially suppressed by the primary queen's pheromone but not entirely arrested. These individuals live within the colony, indistinguishable in behavior from workers, their reproductive potential held in chemical suspension. If the primary queen dies, or if a section of the colony becomes physically separated from her pheromone influence through damage to the mound flooding or deliberate disturbance, the nearest neotenic reproductive activates. Her suppression lifts. Her reproductive organs develop. Within days, she begins laying eggs. The colony does not skip a beat. Succession has occurred chemically and automatically without crisis or competition in the time it takes a human organization to schedule an emergency meeting. The queen is irreplaceable only in the sense that she is always already being replaced quietly and visibly in the body of someone standing right beside her. The queen is simultaneously the ruler of the colony and its prisoner. She is the most important individual in a structure housing millions. She is groomed continuously. Workers lick her body surface, removing pathogens and debris, maintaining the cuticular health of an organism whose death would trigger immediate colonial crisis. She is fed constantly, pre-digested food delivered mouth to mouth by workers in steady rotation. Her eggs are removed almost as quickly as she produces them, carried to nursery chambers by relay teams that never pause, and she cannot move, cannot leave, cannot in any physical sense participate in the life of the colony she governs. Her world is a chamber roughly the size of a shoe, deep underground in total darkness, surrounded by workers whose entire biological purpose is to sustain her. She has not seen the mound she built. She has not walked the tunnels her workers excavated. She will die in the room she has occupied for decades, attended to the last by individuals who do not know she is dying, and who will begin quietly and chemically to replace her before her body is cold. Termites share food in a way that doubles as chemical communication. Trophallaxis, the mouth-to-mouth transfer of liquid food between colony members, is not merely a feeding mechanism. Every exchange carries chemical information embedded in the transferred fluid. Pheromones produced by the queen distributed through workers who have fed directly from her, spread through the colony via this network of food sharing, reaching individuals who have never been in the queen's physical presence, conveying her reproductive status, her health, and her chemical identity to every corner of the Bruss mound. The same network carries alarm compounds, caste regulation signals, and colony identity markers. A termite that receives food from a nestmate receives not just energy, it receives a chemical update on the state of the colony. The feeding network is simultaneously the colony's digestive system, its immune communication system, its social regulatory mechanism, and its news service. Every meal is a message. Every exchange is a broadcast, and the information moves through the colony continuously, in every direction, carried by individuals who have no idea they are transmitting anything at all. The colony responds to seasons without any individual termite knowing what a season is. As temperature and humidity shift with the changing seasons, the termite colony adjusts, expanding foraging activity in warm, moist periods, contracting it in cold or dry ones. Fungal garden management intensifies before the dry season and relaxes as rains return. Reproductive activity accelerates in the weeks before the annual elate swarm, triggered by specific combinations of temperature, humidity, and barometric pressure that the colony reads collectively through the aggregated responses of millions of individuals, each sensitive to a narrow slice of the total environmental signal. No termite understands the concept of a season. No termite knows that it is preparing for a dry period or a rainy one. Each individual responds to local conditions, and the sum of millions of local responses produces a colony-level seasonal rhythm as reliable as a calendar. It is one of the clearest demonstrations in nature that collective behavior can produce outcomes no individual contributor could comprehend, plan, or even be aware of. The colony knows what no termite knows, and it acts accordingly, every year, without fail. In times of starvation, the colony eats its own soldiers. When food sources fail during severe drought, after a colony has been displaced, or during the slow decline of an aging queen, the termite colony faces a brutal metabolic equation. Soldiers fed exclusively by workers and producing no food themselves become a caloric liability the colony can no longer sustain. In documented cases of colony starvation, workers have been observed killing and consuming soldier nestmates, cannibalizing the defensive caste to sustain the productive one. It is not disorder. It is not breakdown. It is in the cold arithmetic of collective survival, the correct decision. Soldiers are the colony's most expensive maintenance item in times of plenty. In times of scarcity, that expense becomes untenable. The colony does not mourn this. The soldiers, following the same chemical logic as every other termite in the mound, do not resist. The calculation is made at the level of pheromone ratios and hunger signals distributed across millions of individuals, resolving into a collective action that no individual chose and no individual could have prevented. The colony survives, and the soldiers, to the end, serve it. The colony's final act before it ends is to send its children into the world. As a termite colony ages, its productive capacity gradually declines. The queen's egg output slows, worker populations thin. The mound requires more maintenance than the shrinking workforce can provide. But before the colony fails entirely, it invests its remaining resources in one last act of extraordinary biological purpose: the production of alates, winged reproductive termites, destined to leave the colony, find mates, shed their wings, and establish new colonies elsewhere. The alate production surge draws on the colony's last reserves of energy and nutrition. The final generation raised with a care and completeness that the colony can no longer sustain for itself. They are fed generously. They are groomed. They are held within the mound until exactly the right conditions arrive, a confluence of warmth, humidity, and barometric pressure that the colony reads with the same distributed sensitivity it has always used. And then they go. They pour from the mound in their thousands into the light and the open air, carrying the colony's genetics and its chemical identity into a future the dying colony will never inhabit. It is not a death. It is a dispersal. And somewhere in the soil beneath a field or a forest or a garden you have walked past 1,000 times, one of those pairs has already landed, shed its wings, and begun to dig. The alate swarm is one of nature's most precisely timed events. Across an entire region, termite colonies of the same species will release their winged reproductives within hours of each other, sometimes within minutes. The synchronization is not coordinated between colonies. Each colony reads the same environmental signals independently: a specific threshold of temperature, a specific humidity level, a barometric pressure drop consistent with an approaching weather system, and arrives at the same conclusion simultaneously. The result is a swarm event that can involve millions of winged termites from dozens of separate colonies filling the air above a landscape at once. The timing serves a purpose. By flooding the environment with reproductive simultaneously, each individual elate's chances of finding an unrelated mate essential for genetic diversity increase dramatically. Predators, however, numerous, cannot consume every individual in a swarm of millions, and the brief window of synchronized emergence triggered by weather ensures that the swarm occurs when conditions are most favorable for the founding pairs that survive. The colony does not know it is running a statistical survival strategy, but it is. After landing, the alate pair performs one of biology's most deliberate rituals. When a male and female alate land after their dispersal flight, they undergo a behavior called dielation, the deliberate shedding of their wings. Wings are broken off at a preformed fracture point near the base, sometimes by the termite's own legs, sometimes against a surface, sometimes assisted by the mate. The shed wings are left behind a small pile of translucent fragments that is often the first visible sign a homeowner notices of a new termite presence indoors. Dielation is irreversible. The termite will never fly again. It is committed physically and permanently to the ground beneath it, to whatever is below the spot where it landed. The male follows the female as she searches for a suitable founding site, maintaining contact through pheromone signals until she selects a location and they begin excavating together. They are at this moment the entire colony. 2 individuals. No workers, no soldiers, no structure, just soil darkness, and the accumulated genetic instruction of 250 million years of successful founding, driving them downward into the earth to begin again. The founding pair survives its first months on nothing but their own bodies. The early weeks of a new termite colony are, by any measure, an extraordinary feat of biological endurance. The founding king and queen, sealed into a small founding chamber they have excavated together, receive no food from the outside. No workers exist yet to forage. No fungal garden has been established. The pair survives entirely on metabolic reserves stored in their own tissues, including the now useless flight muscles that powered their dispersal flight, which are broken down internally and recycled as energy. The queen begins laying her first eggs within days of founding. The king fertilizes her. They tend the eggs themselves, grooming them, repositioning them, protecting them from the desiccation that would kill them in an unattended chamber. The first workers that hatch are fed by the queen from her own metabolic reserves, glandular secretions produced at considerable cost to her already depleted body. The colony that will one day house millions begins with 2 exhausted insects eating themselves to feed their first children, in a chamber the size of a grape in total darkness with no guarantee that any of it will work. Some termite queens reproduce without a male. Parthenogenesis, asexual reproduction in which females produce offspring without fertilization, has been documented in several termite species, most extensively in Reticulitermes species, studied in Japan and Europe. In these cases, queens produce female offspring from unfertilized eggs, while fertilized eggs produce workers and soldiers. The unfertilized offspring are genetically identical to the queen, her reproductive insurance against the loss of the king. If the king dies and no replacement is immediately available, the queen can maintain colony growth unilaterally, producing a new cohort of potential replacement reproductives from her own genetics alone. The discovery of parthenogenesis in termites complicated what researchers had previously assumed about the necessity of the king and raised new questions about the genetic structure of long-established colonies. Scientists studying colonies with evidence of extended parthenogenetic periods found genetic patterns in the worker population that suggested the queen had been reproducing without fertilization for years before the behavior was detected. She had not announced the change. The colony had not noticed. She had simply continued as she always had, producing. The termite colony has been compared to a brain, and the comparison is more than poetic. The parallel between a termite colony and a neural network has been drawn by researchers in both fields, and the structural similarities are on examination genuinely striking. Individual termites, like individual neurons, have no understanding of the system they constitute. Each responds to local inputs, chemical signals from immediate neighbors, physical cues from the immediate environment and produces a local output. No individual has access to global information. No individual makes colony-level decisions. Yet the aggregate behavior of millions of locally responding individuals produces outcomes, architectural decisions, foraging strategies, defensive responses, caste regulation that are globally coherent, adaptive, and in many cases optimal. Neuroscientists studying collective cognition have used termite colony models to explore how intelligence emerges from non-intelligent components. The termite colony does not think in any sense that maps onto individual consciousness, but it produces outcomes that if a human organization produced them, we would call thinking. And the gap between those two statements, between producing thought and being a thinker, is one that science has not yet cleanly closed. Termite colonies can solve spatial problems without any individual understanding the problem. In a series of experiments conducted by researchers studying collective intelligence, termite colonies were presented with foraging challenges, food sources accessible only through maze-like obstacle courses, and their performance was measured against random search models. The colonies consistently outperformed random search. They found the most efficient routes faster than probability alone would predict. They allocated foraging effort in rough proportion to the richness of different food sources. They avoided dead ends more reliably than chance would explain. No individual termite navigated the maze. No individual assessed the options. The colony's performance emerged from the aggregated trail-laying and trail-following behavior of thousands of workers, each responding only to the pheromone concentration at its current location. The maze was solved by a process that looks from the outside like intelligence and is from the inside nothing more than chemistry and movement. Scientists still debate where the boundary between those two descriptions lies. The termites characteristically have no opinion on the matter. The queen changes, and so does the colony over decades. A termite queen does not remain chemically static across her multi-decade lifespan. Researchers who have analyzed the pheromone profiles of queens at different life stages have found measurable shifts in the composition and concentration of the chemical signals she produces as she ages. These shifts are not random, they correspond to changes in colony behavior. Younger queens produce pheromone profiles associated with rapid expansion, high worker production, aggressive foraging, accelerated construction. Older queens produce profiles associated with consolidation, more moderate growth, greater investment in soldier production, and an earlier than usual surge in reproductive output. The colony reads these changes and adjusts. It is, in the most literal chemical sense, being managed differently as the queen ages, her body communicating a life stage strategy to millions of individuals who respond to it without awareness that anything has changed. The colony ages with its queen, and when the queen's pheromone profile finally begins to fade, when the signal grows thin and inconsistent, the colony reads that too, and begins, quietly, to prepare for what comes next. The average worker termite lives for less than 2 years, but its function is eternal. Individual workers are temporary. The role they fill is not. As one cohort of workers ages and dies, the next cohort raised in the nursery chambers, inoculated with gut microbiome through trophallaxis, chemically calibrated to the colony's current needs, steps into the same tunnels, performs the same tasks, follows the same pheromone maps, and extends the same structure that the previous generation maintained. The colony does not experience this as loss. There is no mourning, no adjustment period, no institutional memory that must be transferred. The chemical environment of the colony is itself the institutional memory, and it persists intact and continuously refreshed, regardless of which individual bodies are currently reading it. A tunnel built by workers who died a century ago is maintained today by workers who have never known a different tunnel. The mound that stands for 1,000 years is not the same mound that was built. It is a continuous process, wearing the form of a mound, sustained by the unbroken chain of individuals who have lived and died inside it, each one replaceable, none of them replaced. Scientists still debate whether a termite colony should be classified as an individual organism. The question is not rhetorical, it is a live, taxonomic, and philosophical issue in contemporary biology. The concept of the superorganism, first proposed in the early 20th century and substantially developed in subsequent decades, holds that some colonial insects, including termites, ants, and certain bee species, constitute biological individuals at the colony level rather than the individual level. Under this framework, a termite is not an organism any more than a single cell is an organism. It is a component of a larger biological entity that feeds, grows, reproduces, and responds to its environment as a whole. The colony has a metabolism. It has a reproductive system. It has an immune response. It regulates its internal environment. It responds adaptively to external threats. Every criterion we use to define an individual organism applies at some level to the colony. What it lacks, what keeps the debate open, is a nervous system, a unified sensory apparatus, and anything that resembles individual consciousness. Whether those absences disqualify it from individuality or merely describe a different kind of individuality than the one we are used to is a question that biology has not yet answered and may not answer soon. To stand beside an active termite mound and truly understand what is beneath you is to feel something shift in how you think about intelligence itself. The mound rises from the ground with a solidity that feels almost architectural. It has been here longer than the trees around it. It will likely be here after they fall. Beneath the surface right now, millions of blind individuals are moving through tunnels they did not design, responding to signals they do not understand, maintaining a structure they will never see from the outside, serving a queen they will never consciously acknowledge, building a civilization they do not know they are building. And the civilization works. It has always worked. It worked before the first human sat beside a fire and wondered what it meant to be alive. It will work in all probability long after the last human stops asking. There is something in that, something that sits quietly at the edge of comfort, the knowledge that intelligence, as we define it, as we prize it, as we build our entire sense of species worth upon it, may be far less necessary to the project of civilization than we have ever been willing to admit. The termite does not think, and yet here is the mound. Here is the empire. Here it stands. Without termites, tropical forests would drown in their own dead wood. In the great forest ecosystems of sub-Saharan Africa, the Amazon basin and Southeast Asia, dead wood accumulates constantly fallen trees, broken branches, root systems abandoned by dying plants. In temperate regions, this material decomposes slowly through the action of fungi and bacteria over years or decades. In the tropics, the pace of decomposition must match the pace of production, and termites are the primary reason it does. Studies conducted across multiple tropical forest sites have found that termites account for a substantial proportion of dead wood decomposition in some sites, the majority of it. Remove termites from a tropical ecosystem, and the forest floor begins to accumulate woody debris faster than any remaining decomposer can process. Nutrient cycling slows, soil fertility declines. The living plants above, dependent on the continuous return of nutrients from decomposing material, begin to suffer. The forest does not collapse immediately, but it begins slowly and measurably to decline. The creature that dismantles your home is also in the ecosystem. It evolved for the engine that keeps the forest alive. Termite mounds make the soil around them dramatically more fertile. The relationship between a termite mound and the landscape surrounding it is not merely structural, it is nutritional. As termites excavate, they bring mineral-rich subsoil to the surface, mixing it with organic material in ways that alter the chemical composition of the surrounding ground. The mound itself, over its lifetime, accumulates concentrated organic matter, fungal biomass, termite fecal material, food processing residues, that is gradually incorporated into the surrounding soil as the mound weathers and erodes. Field studies conducted in African savannas have found that soil within a short distance of active termite mounds contains significantly higher concentrations of nitrogen, phosphorus, and potassium than soil further away. Plants growing near termite mounds are measurably larger, healthier, and more productive than those in the surrounding landscape. In dry years, when vegetation across the savanna browns and thins, the area around a termite mound frequently remains green, a fertility island in a landscape of stress, produced by the accumulated work of an underground empire that has no awareness of the gift it is giving. Abandoned termite tunnels become the water infrastructure of entire landscapes. When a termite colony dies, relocates, or contracts, it leaves behind a network of sealed tunnels extending meters below the soil surface. These tunnels do not disappear. They persist, sometimes for centuries, as hollow channels through otherwise compacted soil. When rain falls on landscapes riddled with abandoned termite infrastructure, the water does not run off the surface or pool uselessly. It finds the tunnels. It follows them downward, percolating through the soil profile far faster and far deeper than it would through undisturbed ground, recharging the groundwater table with an efficiency that hydrologists studying semi-arid landscapes have found both measurable and significant. In regions of East Africa and South Asia where rainfall is seasonal and groundwater recharge is critical to both ecological and human survival, the contribution of termite tunnel networks to subsurface hydrology has become a subject of serious research interest. The termite digs for its own reasons: moisture access, colony expansion, foraging reach. It leaves behind, without intention and without awareness, a water management system that entire landscapes depend on. Termite mounds support hundreds of other species long after the termites are gone. An active termite mound is already a biodiversity hotspot. Its stable temperature, humidity, and nutrient content attract a community of guest species that shelter, feed, and reproduce within its structure. But the mound's ecological value does not end when the termites do. Abandoned mounds, their clay walls still standing, their chamber network still intact, become habitat for an extraordinary range of secondary occupants. Reptiles use them as nesting and basking sites. Burrowing owls and other cavity-nesting birds excavate chambers for breeding. Small mammals shelter in the lower galleries during dry seasons. Invertebrates colonize the nutrient-rich mound soil for years after the original colony is gone. In some African ecosystems, the distribution of abandoned termite mounds across the landscape has been shown to predict the distribution of several vertebrate species animals that depend on the mound's physical legacy, even though they never encountered the termites that built it. The mound outlasts its builders, and in outlasting them it continues to serve a landscape that has organized itself over millions of years around the assumption that the mounds will be there. Termite mounds become refuges when everything else dies. During drought, the defining ecological stress of the semi-arid regions where the largest mound-building species thrive, the mound's deep foundation and passive climate control create a microenvironment that persists long after the surrounding landscape has dried beyond the tolerance of most life. The deep moisture access that allows the colony to survive also maintains humidity levels in the mound's lower chambers that support a microhabitat dramatically cooler and wetter than the air above. Insects, spiders, small reptiles, and occasionally small mammals retreat to termite mounds during severe drought events, sheltering in chambers or in the mound's outer crevices, waiting out conditions that would kill them in the open. Field researchers in the Kalahari and the Australian outback have documented this refuge effect repeatedly, recording species diversity at active and recently abandoned mound sites that far exceeds the surrounding landscape during dry periods. The mound that the termites built for themselves becomes in extremity a shelter for everything around them, built without generosity, occupied without invitation, essential without intent. Where termite mounds cluster, plant diversity follows. One of the more striking discoveries in termite ecology over the past several decades is the relationship between termite mound density and plant species diversity at the landscape scale. In African savannas where mound-building termite species are abundant, satellite imagery and field surveys have consistently found that areas with higher mound density support greater plant diversity, more species, more structural complexity, more layered vegetation than comparable areas with fewer mounds. The mechanism is the fertility island effect described earlier, operating at a landscape scale. Each mound creates a patch of elevated soil fertility. Each patch supports a slightly different plant community than the surrounding savanna. Across dozens or hundreds of mounds in a given area, the mosaic of fertility patches produces a landscape far more biologically diverse than uniform soil chemistry would generate. Ecologists studying this pattern have described termite mounds as biodiversity generators, physical structures that produce ecological complexity simply by existing without any intention, without any awareness, and without any investment in the outcome beyond the colony's own immediate survival. Termite mound soil may help clean up humanity's chemical mess. Among the more unexpected applications of termite biology currently under investigation is the use of mound soil in environmental remediation. The microbial communities that accumulate in termite mound soil over decades of colony activity are by any measure extraordinary, diverse, metabolically active, and capable of processing a wide range of organic compounds. Researchers studying mound soil samples from several African and Asian species have identified bacterial strains capable of degrading petroleum hydrocarbons, chlorinated solvents, and certain agricultural pesticide residues, compounds that persist in contaminated soil for decades and resist conventional remediation approaches. The precise mechanisms vary by compound and by bacterial species. The practical applications are still in early development, but the basic finding that the biological engine running beneath a termite mound produces microbial tools capable of breaking down some of the most persistent pollutants humanity has introduced into the environment carries a particular irony worth noting. The insect we have spent decades trying to eliminate with chemicals may, in the end, help us clean up the chemicals we have left behind. The methane termites produce is part of a cycle, not just a problem. Termite methane emissions have appeared in climate discussions as a negative, a natural greenhouse gas source contributing to atmospheric warming. The reality is more nuanced. The methane that termites produce through hindgut fermentation enters an atmospheric carbon cycle that has been operating in rough equilibrium for as long as termites have existed, which is to say, for a very long time before human industrial emissions altered the balance. In undisturbed tropical ecosystems, termite methane is offset by the carbon sequestration of the forests. The termites help sustain through decomposition and soil fertility. The carbon the termite releases as methane is in many cases carbon that was recently fixed by the same forest whose dead wood the termite is breaking down. It is a loop, not a leak. It is that the ecosystem's buffering that methane are shrinking. Deforestation removes the carbon sink without removing the termites. And a natural cycle interrupted becomes something else entirely. Something less balanced, something more difficult to repair. Humans have been using termites and learning from them for thousands of years. Across sub-Saharan Africa, South Asia, and parts of South America, termite mound clay has been incorporated into human material culture for millennia. Its exceptional hardness and thermal properties made it a preferred material for constructing cooking hearths, grain storage vessels, and the walls of traditional homes in regions where it was abundantly available. In parts of West Africa, termite mound clay is still used in pottery and construction today, valued for properties that modern materials scientists have only recently begun to formally characterize. Indigenous communities in Brazil, Nigeria, and India have documented medicinal uses of termite mound material, applying it to wounds, using it in treatments for digestive illness, incorporating it into practices whose pharmacological basis is only now being investigated by researchers who find more often than not that the biological rationale for the traditional use turns out to be sound. The communities living closest to termite mounds have understood their value longest. Science is arriving, as it often does, to confirm what practice already knew. The creature that eats your home alive is also quietly building the world you stand on. It has been doing this since before the first flower bloomed, since before the first bird flew, since before the first mammal drew breath in a world that had until that moment belonged entirely to older things. It does not know this. It has never known anything in the way that knowing requires a self to hold the knowledge. It moves through its tunnels in total darkness following chemistry, building without blueprint, farming without understanding agriculture, waging war without understanding conflict, sustaining a queen it will never see, maintaining a structure It will never perceive as a whole. And yet the mound stands. The forest cycles. The soil deepens. The water table holds. The landscape organizes itself around the assumption that this empire will continue. Because it always has, because nothing in the long history of life on this planet has yet found a reason sufficient to stop it. We spray it, flood it, poison it, bulldoze it, and somewhere beneath a field you have walked past, somewhere beneath a garden you have tended somewhere, beneath the foundation of a house that looked perfectly fine from the outside, it is already rebuilding. Patient, blind, chemically perfect, ancient beyond any honest reckoning, and entirely completely indifferent to what we think of it. That is the termite, that is the empire. And it was here long before us, and in all likelihood, it will be here long after. Good night.